In this video, we'll be looking into one of the most crucial aspects of Internet of Things, that is processing topologies and its types. So we'll look into the data formats which are used in IoT, what is the importance of processing in IoT, what are the processing topologies, and what are the design considerations and selection considerations to be made use of, and we'll also look into one of the most important topics, that is processing offloading. So let's start from the first topic here. So the first topic which we have here is data format. Data format means it will tell how the data is organized, stored, and accessed in any system. So we speak of organization, storing, and accessing of data in an IoT system. That's what is referred as data format. In IoT, vast amount of data is generated by various sources like sensors, devices, users, and monitoring systems. So as we know that sensor will detect any particular thing from the environmental stimuli and convert it into the any action which is required using actuator. But this conversion does not happen directly. It we make use of network to transfer the data, and once the data which is accessed here needs to be processed also. So in order to perform all these operations, data is very important, and understanding the data format is again very crucial. So proper data formatting will help us to see the data is efficiently processed, analyzed, and utilized. So looking at the role of data formatting in IoT applications, first one we have is efficiency. IoT systems will generate large amount of data. So properly arranging the data or properly formatting the data will make it easier to access it, process it, and utilize it. Then we have interoperability. That is, many different IoT devices and applications make use of or make use of the same database, right? Or store the data in same database. In that case, it should be operatable in different systems also. That is, standard data format should be followed, which will help in communication, which will help in data transfer efficiently. Storage and management means, so see, through data formats we understand how the data is stored. This will also tell us what is the choice of database which we are using. It could be structured, it could be SQL for structured data, or NoSQL for unstructured data. Then we have data integrity. Data integrity means only when we have well-defined formats, it will help us to capture the data properly. That is, there won't be any errors or redundancies happening here. So this was about the role of formatting in IoT applications. Now we'll look into this figure here. So figure 6.1 tells us about the various data generating and storing sources connected to the internet and plethora of data types contained with it. So if you can see here, we have internet and cloud. That is, yeah, through internet and cloud, these will serve as the primary hub for data storage and transfer. It will also help to transfer the data between the users and the cloud, right? That is primary hub for data storage, how info is transferred between users and devices. Then we have human data resources. Human data resources are the data which is transferred through emails, social media posts, or any videos, anything. Next we have is non-human data resources. Non-human data resources could be the sensors which are being used here, or it could be the industry, transport, buildings, traffic, transaction. All these come under non-human data sources. So this diagram highlights how various data sources, it could be the humans or it could be the machines, contribute to the global IoT ecosystem. This is the global IoT ecosystem, thereby generating different types of data. Here different types of data are being generated, and these data which are generated are also stored efficiently. Next topic which we have is types of data format in IoT. So depending upon the structure, there are two major types of data formats. One is structured data and the other one is unstructured data. Let's look at the differences here. So first definition for structured data, data that has predefined structure or format. This will have structure, this will not have any particular specific structure. Speaking of storage, so in order to store the structured data, we'll be making use of relational database management system, RDBMS. In order to store the unstructured data, we'll be making use of NoSQL databases. Next, looking at the format, for structured data, there'll be fixed size, there'll be fixed rows and columns and all. Speaking of unstructured, there is no specific format. We can store text, images, videos, or anything. Coming to example, phone numbers are all integer data type, and social security number again integer data type, bank records again integer data type. So when you're storing data in structured data, structured table, you'll be making use of similar data type. all these definitions or differences are self-explanatory because we have understood or studied these topics, structured and unstructured in DBMS um, concept, right? So examples here are these, and for unstructured, it could be email, images, videos, audio, recording, sensor data, and so on. Searchability. In terms of structured data, it becomes easy to search because we are making use of queries here, that is SQL. Whereas when it comes to unstructured data, it is a little difficult to search because only if we have the advanced algorithms or tools we can search. If not, we cannot search. Coming to it is generated by structured data could be the human or machine generated, but in fixed fields is that is we know int 5 or char 5, that is character type of length 5. Coming to unstructured, it is mainly human generated, that is text, media, or it could also be machine generated. Usage examples. Structured data is used in bank, reservation systems, inventory control, whereas unstructured data, NoSQL topic, it is used in social media, IoT sensor data, surveillance footage, and so on. Query language is SQL here, and here it is NoSQL. IoT data share. Speaking of IoT data share, we can say that structured data will have minor share, whereas unstructured data will have major share. Unstructured data will have major share because whatever the data you are accessing through the sensors need not be of same data type. If suppose let's say from the temperature sensor you'll get one type of data, and from the moisture sensor you'll get another type of data. Are these two data of same format? I don't think so. In that case, we'll be making use of unstructured data. Okay, that's what the difference here speaks of. So moving on further, why does this matter in IoT? So processing challenges. So speaking of examples of NoSQL database like MongoDB, Elasticsearch, they are preferred as they can handle varied and large data sets. Next, we have searchability and flexibility concepts. That is, when we make use of unstructured data, it is flexible, but searchability becomes difficult without any algorithms. Right. Next, moving on further, we have importance of processing in IoT. So we can say that in IoT applications, large amount of data and diverse types of data is stored here. Right. So IoT is growing. So there is high need to process the data and convert it into meaningful insights. So processing will make sure that data from the IoT devices is converted into some valuable information which can be further used by the actuators to perform the action. So it is processed info should be real time decision making, and it should support optimization, and it has to contribute towards efficiency. Looking at the key considerations in IoT data processing, we have two key considerations: when to process the data and what to process the data. So these decisions depend on the type of data and the urgency. So if you feel that a particular data is very important, very time critical, then it has to be addressed first. So that is what further we have. Data processing in IoT is categorized into three types. First one is very time critical data, and normal data. Let's look at these one by one. So the first one which we have is very time critical data. Here examples could be healthcare, life support system, flight control system, and so on. So speaking here, immediate decision or action should be taken place. Here the priority should be this sort of data should get the priority processing, and here data must be processed close to the source. If the data is processed close to the source, no, it can send the response back quickly, and thereby actions can be taken place accordingly. Then minimum latency, that is once I send some data, there should not be once I send a data, it should be quickly accessed here. That is, latency should not be there here. Minimum latency should be there. If minimum latency is not there, suppose if we are speaking of healthcare system, if a patient's pulse rate is being measured, the patient's pulse rate is being measured, and it has to be processed and displayed on the monitor here. So if the latency is high here, then displaying will take a lot of time. When displaying is taking a lot of time, the doctors may not be able to decide anything. So processing latency must be within milliseconds. So here within milliseconds it has to be processed. So that's what we speak about very time critical data. Next we have is time critical data. Time critical data means data may be processed remotely, that is in cloud computing. So speaking of this, here we come across edge computing topic. Edge computing, that is right next to the sensors, it has to get processed. Okay, we'll study this edge computing, cloud computing in further topics. So here time critical data. data may be processed remotely. It may not be the data which you have fetched from, let's say, traffic. Okay, so the traffic CCTV cameras has acquired some data, right? So this data need not be processed there itself in the traffic signal. It can be sent to the data processing system, the data processing center, and from there further insights can be developed. That's what we speak about. Data may be processed remotely. So urgency, but it is lower than very time critical data. So processing of this data is very important. Let's say signal processing. So through CCTV camera sensors will get to know that in this time it is very traffic is there or traffic is not there, and accordingly the change of traffic signal should happen, right? So it is urgent, but compared to very time critical data, it is not that prioritized. So it allows us for collaborative or distributed computing. Examples are vehicle systems, smart home machine systems, smart traffic management, and so on. So here latency could be up to seconds. So latency could be up to seconds, whereas speaking of the very time critical data, it is in milliseconds. Moving on further, we have normal data. Normal data means it does not require any immediate attention or action. So it can be processed leisurely. So it makes use of centralized server or cloud solutions. Example could be agricultural monitoring. Suppose you are making use of soil moisture sensor. So it is not very important to process the data and give outputs, right? So it can be processed leisurely, taking up some time. It could be minutes or hours. The processing time can go on, right? Next topic. This was all about the three data types and importance of processing in IoT. Moving on further, we have processing topologies and IoT. Processing topologies in IoT are very important to determine how the data is collected, how it is handled, processed, and utilized. So the proper selection or proper topology will result in significant savings. That is, it could be in terms of the bandwidth, energy, and the infrastructure cost also. It will also reduce the latency when you are selecting the proper topology. Topology means arrangement, right? So proper topology will reduce the time gap also. So processing topologies can be broadly classified into on-site, and the other side we have is off-site. Off-site can be further specified as remote off-site and collaborative off-site. Let's look at these one by one. So the first one we have is on-site topology. On-site topology, data is processed at source itself. The sensor node both collects the data and processes it locally. That is, on site only the data collection is also happening and processing is also happening. It is used in applications which have very low latency tolerance. That is, even with slightest delay, it could lead to large consequences. Suppose, speaking of healthcare, that's what we have discussed above. Patient's pulse rate. When we take patient's pulse rate, it has to be measured then and there by the sensor, and it has to also be processed. So depending on the processing and the output which we get, we can take any immediate action. It is same in flight control system also. So immediate processing and real time decision making are required here. So here the advantage is reduced latency. That is, once it is sensed, at the same time processed, and we get the processed data then and there. So there is latency is reduced here, minimum latency. Looking at the example here, figure 6.2, event detection using on-site processing topology. So here you see the environment, that is, event is detected. The event is fire event, which is detected by the temperature sensor. Then we have sensor node activation. So once the event is detected, the node gets activated to process the sensed data locally. And then we have processing and alert generation. That is, sensor node will process fire event data and generate alert based on predefined conditions. So in that particular sensor node only, you will have sensing element as well as processing element also. Depending on the processing element, there will be predefined actions. That is, if fire is sensed, then turn on the alarm, something like that. Okay. So further action would be taken here. Further actions can be taken place. So this was about on-site processing topology. Next, moving on, we have off-site processing topology. So here the data is collected by the sensor node but processed elsewhere, typically at a remote location such as cloud server. Previously we saw that the sensor was sensing the data and then processing was also happening at the same place. But then here, once the data is sensed, that it is further sent to a remote server or cloud server where processing can happen off site. It is not happening on site, it is happening somewhere else. So offsite processing can tolerate some latency. When you are transferring the data from the sensor to the cloud, of course, it will take some time. So when the time is being taken here, latency is also a issue. So latency, it can tolerate some latency. Less immediate data processing compared to the on-site. Here we can it can be used for less immediate data processing. For example, it could be in the, let's say, agriculture or smart home automation. In such cases where immediate action is not required, we can make use of such topology. So typically cheaper, since processing infrastructure does not need to be on site. So by making use of just simple sensors which has only one function, that is to just sense, and after that sending the data to the cloud, we are saving the resources here. So we are not making use of, for each sensor there will be a processing unit. No, that is not required here. So you are saving money here. It is scalable in IoT large deployment. Speaking of large IoT systems where each sensor cannot have a processing, you can make use of such topology. Okay. Looking at the different types further here, we have remote processing. Remote processing is one of the most common types of offsite processing dat where data from multiple sensor nodes is forwarded to the remote sensor or remote server, or it is also called as cloud infrastructure, remote server or cloud infrastructure for processing purpose. So this allows for massive cost and energy savings, because powerful processing platforms can be shared among many smaller nodes, right? There could be multiple smaller nodes and one big processing node. So these all can share the data here, and processing can happen there. So resource sharing and scalability are two advantages here. Looking at the example here, here you can see that the event detected is fire. Fire is detected by the temperature sensor. Sensor node sensing, the sensor node collects event data but does not process it locally. Here, although it is collected, it is not processed locally. It is transferred to the remote server or remote cloud through internet. So data transmission happens through internet. Further, at this position, the processing and decision making takes place, and further, whatever the result comes, it will be taken as the actuator action. So this was about remote processing. Moving on further, we have collaborative processing. Collaborative processing is used in scenarios where there is limited or no network connectivity. Okay, so sensor node collaborates by pooling their processing power to handle locally without the need for remote processing infrastructure. So this can be used in large scale IoT deployments where a network is not properly available. For example, rural environments or agriculture, a large scale IoT deployment. Let's look at the example. Let's look at the figure here. So here we have the event, that is a fire is detected by the temperature sensor. Next we have is the temperature sensor, that is detecting the temperature. Next here we have is collaboration among nodes. That is multiple nearby sensor nodes will collaborate. Multiple nodes will collaborate with each other and process the data here locally. It will process the data, either he can process or he can process or the other node can process. So here the connection is happening through mesh topology. Okay, in mesh topology arrangement, all the nodes are being connected here without relying on the remote server. So here internally they can process the data without having the need of remote servers. So once the data processing and decision making happens, the sensor node will send the particular output and further actions can be taken. So speaking of the key benefit, here it is self-sufficiency, and it has the ability to reduce the network traffic. So network traffic reducing this would be important in areas with limited connectivity. Right, it can also save or conserve the bandwidth and reduce the latency compared to the remote processing. So here we come to an end between the differences, IoT device design and selection considerations. So when we are designing a IoT solution, it is very important to select the right processor, right? Because only if you select the right processor, you can like the system's performance is affected, right? So the usability or the design, affordability, energy efficiency, all these factors or all these various facets are being impacted by the selection process. So let's look into the key considerations which are to be taken into consideration while selecting a processor for our IoT system. So the first one we have here is size. That is, the size of processor influences or decides the form factor. So size is directly dependent on the form factor. Form factor means larger the form factor, higher would be the energy consumption. So depending on the devices, the size of processor is varying. Suppose if I'm taking wearable device, smartwatch. So for a smartwatch which I'm wearing on my hand, tell me should the energy consumption be less or more? So when we are speaking of wearable devices, energy consumption should be less here. So any processor which has less energy consumption should be taken into consideration. Less energy consumption means small form factor. Small form factor means yeah, the size is small form factor here. This was about energy. Next we have is energy again. Energy efficiency is crucial in IoT applications. So processor having higher energy consumption will have frequent charging, battery replacements, and it affects the sustainability of IoT system. So let's take a low energy processor. It will have long term and remote applications. That is, if we are speaking of a sensor which is placed in glacier, so this sensor should have a low energy consumption because you cannot change the battery again and again, right? So speaking of the harsh conditions, you cannot go there and change the battery every now and then. In such cases, processors having low energy or energy efficiency should be taken into consideration. Next, we have is cost. So the cost of processor and the sensor affect the scalability of IoT solutions. That is, affordable processors will allow high density deployment, that is making them more accessible for widespread applications. Here examples could be the fire detection or gas detection. Next we have is the memory. Memory, again we know both volatile and non-volatile memory determine the device's capability to process the data, store the data, and manage the data. So devices which have more memory offer more functionalities. Any processor having more memory will offer more functionalities, that is data processing happening locally. Or and not just that, it is little expensive when it comes to when I'm taking a memory which is having which offers more functionalities. Of course the price will also be more, right? So the processing power of device is very important, especially when we are dealing with any data, any systems which has large data or complex data applications. For example, it could be video processing or image processing. So higher the processing power, more complex tasks and data intensive tasks could be performed here easily. Next we have is the IO rating. So input output voltage rating, it affects the circuit's complexity and energy use. So modern processors have lower IO rating, that is compared to the older ones. Suppose if a particular device or a processor has IO rating of 3.3 volts, this is for the older version. For the newer version, it could be very less, or compared to that, it could be 0.5 something. I'm not sure about it. Next we have is the add-ons. Add-ons here would be the extra. The add-ons could be the extra features like analog to digital conversion units, clock circuits, USB, Ethernet connections, or any other features. So these things, no, this will speak about the flexibility, that is robustness to the IoT solutions. So processing offloading is one of the very important concepts that is usually asked in exams. So make sure you understand this properly. So processing offloading means shifting the computational load from the resource constrained device, from the sensor, for example, from the sensor, and moving it to the powerful external sources. That is, it could be the edge services or fog nodes, remote server, or cloud. So here, see, basically instead of performing the processing in the sensor itself, you're just shifting the processing load here. So that's what processing offloading definition stands for. So the goal is to keep the IoT devices simple, energy efficient, low cost, while making them perform complex tasks. So in order to achieve all these, we can make use of offloading heavy computations to the external systems. So advantages here are scalability, saving the energy, and minimizing the hardware cost. So looking at this diagram, let's understand this. So this figure represents the typical IoT deployment. It will tell us how the data is generated, processed, and transmitted across different layers. That is, from the local processing to the cloud-based processing, through edge processing and fog processing. So the first topic which we have here is sensing layer. Sensing layer is here, right? So in sensing layer, sensors like it could be the temperature sensors or any other sensor will collect the data right? It will collect the data from the environment, and in some cases processing can happen here locally. That is, it can be processed here if the data is very small and time critical data, then it can process here locally, where the sensor is directly integrated with a processor. Here local processing is done only for on-site, for very time critical sensitive applications. We have discussed what are the very time critical data, right? We have discussed it here. Next, moving on further, we have is the edge processing. So data from the sensors can be processed onto the nearby devices within the local network. This is within the local network only. Here it is short range wireless network. Okay, so the edge layer processes the data which is closer to the source, thereby reducing the data transmission to the cloud or to the fog. So here the processes involved here could be filtering or manipulating the data and so on. So here the communication mostly happens through short range wireless communication. That's what we have discussed. Next we have here is fog processing. Fog processing means fog nodes will handle processing at intermediate layer, which is between the local layer and the cloud. So this is the intermediate layer between the local and the cloud, right? So here the processing will happen. So this will offer this particular layer or processing will offer faster response time compared to cloud processing, because comparatively they are closer, right? Comparatively they are closer to the sensor, right, or the data source, yet they are outside the sensing layer, right? Yet they are outside the sensing layer. So fog processing helps us to reduce the latency and network bandwidth usage. Coming to cloud, okay, cloud processing. So if any additional processing is required, then the data would be forwarded here to the cloud. So here the transmission is through long range wireless networks or long range wireless connections. So cloud processing involves large scale centralized systems which are capable of handling large amount of data. That's why we have written sensors and database here, because they are capable of handling large amount of data. But it is slower compared to the fog processing, or even for that matter edge processing also, because here quickly the data is processed and transmitted back. Here also quickly the data is processed and transmitted back. Whereas when it comes to cloud, there is a certain chain or fashion which needs to be followed in order to acquire the data firstly, process it here, and then send the results back to the actuator. So this is what we can understand from this diagram. So I have written all the points here about sensing layer, edge processing, fog processing, and cloud processing. Now we have three key parts of data offloading. So the first one is offloading location. So where are you offloading the data? Right. Either it could be at the edge or it could be at the fog. I'll show it here. So where are you offloading the data? That is the location. Either it could be at the edge, firstly, it could be at the fog, or there could be any remote server, or it could be at the cloud. Processing is done very close to the source of data generation, that is at the edge of network. For example, if you are taking smart camera which is performing object detection, it would be like detection locally would be edge processing. That is, here the camera is capturing the object, and very close to it smart camera, that is object detection, will also happen here, whereas the output would be detected object without the need of external processing. That is, we are not sending it externally. In order to achieve this, we'll be making use of edge processing. Next we have is fog. Fog means data is processed at fog nodes. Fog nodes will be between the edge and cloud. So taking example smart cities, fog nodes handle traffic data processing, and it reduces the need for cloud communication. Next we have is the remote server. So some IoT applications offload processing to the remote servers. Taking example smart home automation, data is sent to the dedicated server. So here let's take an example, home sensor node would be there. It will sense a particular thing. Suppose let's take the smart lights only. Okay, so smart light sensor is there. Only if I enter the room, sensor will detect something, it will send to the sensor node, and from the sensor node it will be transmitted to the server, the common remote server, from which the processing will happen, and again a particular output or signal would be generated, which will in turn turn the light on, right? That's how it works. Next we have is the cloud. So data is sent to the cloud for more scalable processing, large scale processing, and it has centralized systems. For example, speaking of weather monitoring system, here the environment data is sent to the cloud for like if we have to process the data, analyze the data, and any prediction is happening. Such complex tasks, no, you can do it in cloud. Okay. Next we have is next key we have is offload decision making. So how will you offload the data? There are again we have three approaches here. So the first one, three approaches here. First one is naive based approach. It involves offloading based on predefined rules. So there are a set of rules like always sending the data to the nearest available resource. This can again be a rule. Looking at the example, temperature data from the sensors might be always sent to the closest fog node without considering the network congestion. So let's assume this as a sensor, here again a sensor, and this is the fog node. So always from this sensor the data would be sent here, even though this fog node is having getting the data from 100 sensors also, congestion is happening here actually. But then because we have predefined what to do, how the decision should happen for offloading, it will send directly to the fog node. So this was about naive approach. So it is predefined. Next, bargaining based approach. So it optimizes the offloading by balancing trade-offs between different parameters. Parameters like bandwidth and latency are taken into consideration here. For example, using game theory, IoT systems may allocate more resources to critical tasks and less resources to less critical tasks. For example, camera surveillance, and more critical or high critical tasks could be the healthcare. Then we have learning based approach. So as and when the data comes and the data is transferred to particular offloading is happening, so these decisions are kept into considerations, and by making use of ML algorithms, dynamic decisions are taken depending on the historic data. For example, traffic management under smart cities. So from historic data, we'll learn that at this time there will be peak hour. So depending on that, we can take decisions accordingly. So during evening times, signals can be changed, or the timing of signals could be changed. Next we have is offloading considerations. So in naive based, in bargaining based, we spoke about bandwidth and latency, right? So that is what comes under offloading considerations. So bandwidth means if a network has limited bandwidth, offloading decisions may prioritize smaller data volumes. For example, in farm monitoring system, smaller sensor data is processed locally. Larger data is offloaded or sent to the cloud, right? Next we have is the latency. So critical tasks will have minimum delay. That's what we have discussed. So and lower latencies. So in this condition, the processing will happen at the edge or fog layer, right, level. For example, healthcare or fire detection are the examples. Whereas if we are having larger latencies, then it is not then it can have larger delay. If it is having larger delay, then it may not be critical task. For example, soil moisture monitoring could be processed in cloud also. Immediate output is not required, right? Next we have is criticality. So higher the criticality, priority would be given, and local processing can happen there. For example, healthcare will have higher criticality. If lower criticality, then the data could be offloaded to the server or cloud. Then we have resources. So offloading decisions depend on processing capability of resources. That is, if there are complex tasks, then it can be offloaded to the cloud. If it is very simple, then I can perform it at, locally, or it can be handled at the edge processing. Next we have as the data volume. Data volume means large amount of data, large volumes of data, for example, video data are often sent to the cloud. Whereas speaking of smaller data, like scalar readings, it can be handled locally. So these are the parameters or the considerations which are very important for offloading considerations. So this was all about offloading processing. This is again processing offloading. So again, as I told, very important topic. Make sure you go through the notes properly. The let me know in the comments, and stay tuned. I'll be uploading further videos pretty soon. So yeah, thank you.